Hi, so the next topic we'll deal with is standardized variables. So this can be very useful in regression. Standardized variables are things that you're somewhat familiar with, right? So you've used this routinely when you looked at probabilities using the standard normal table, right? So standardized variable is just the value of the variable minus its mean divided by its standard deviation, okay? And of course, in this case, we can use standard errors, since we're dealing with sample data typically when we run regressions. Okay, so we do this for each observation that we have, right? Every data point. So we have yi star now becomes yi minus y bar over sy, where y bar is the sample mean, sy is the standard error of y, right? Also known as the sample standard deviation. For short, we'll just call it the standard error. We'll do the same for x, right? xi star becomes xi minus x bar over the standard error for x, right? Where y star and x star are the standardized variables. And then we can run our regression as per usual. One thing to note is that in the standardized regression model, beta 1 falls away. In other words, beta 1 hat equals 0 when you run a regression after having standardized the variables in the regression model. The natural question is, why is that? Why does beta 1 hat become 0? And that is if we look at how beta 1 hat is comprised, what beta 1 hat comprises of, it becomes obvious why it equals 0. You have y bar minus x bar. And of course, the mean of both of these variables equals 0, right? So beta 1 hat reduces to 0 in this case. Now, why is this useful? Well, one reason why it's particularly useful, and it's especially useful in multivariate regression, is that all coefficients are interpreted in the same way. In other words, you can compare the relative effect of various coefficients in the regression model, right? And this is something that you'll deal with more in multivariate regression. So I won't spend too much time talking about that. But that interpretation itself is also interesting. Not just the fact that you can compare parameter estimates. The interpretation of the individual parameter estimates themselves is interesting because you now interpret it as a standard deviation. So you can say that in the case of the bivariate model, if x star, where x star is the standardized version of x, increases by 1 standard deviation, on average, y star changes by beta 2 star standard deviations, right? So things are interpreted in terms of standard deviations, and that gives you a sense of the scale of a given change as well, right? In terms of the distribution of the scale. It's not just a sort of absolute value. And again, the ability to compare the relative effect of different parameters is also very useful in a multivariate regression. All right, now let's move on to other functional forms. The functional form just refers to the specification of regressions. Very useful ones are to use log variables, and you'll use this often in macro, as well as in other fields, subfields as well. It's very common to log variables. And of course, when we say log, we mean natural log. So by now, you're all quite familiar and comfortable with how to interpret a beta 2 coefficient for a bivariate regression. So for the example given on this slide, if you have final mark regressed on study hours, and you have a beta 1 hat of 50 and beta 2 hat of 5, then the interpretation is that if study hours increase by 1, then on average final mark goes up by 5, right? Because you have a positive beta 2 hat here. Okay, so that's a standard regression. Now let's look at some different functional forms. So on this slide we have what we call a double log or a log linear model, right? So both variables in this case are logged, okay? And if you have a function that looks like the one grayer, then this is especially useful, right? And these sorts of functional forms do come up from time to time. In fact, the Cobb-Douglas function is one such model that looks similar to this. So the interpretation of beta 2 in this case is that a percentage change in y is associated with a percentage change in x on average. Okay, so here's an example given at the bottom. You have logged quantity demanded equals beta 1 hat, beta 2 hat, and logged times logged price. So the interpretation here is if price increases by 1% on average, quantity demanded decreases by 0.253%. Important thing to note in the log-log model, you don't need to change the scale or the value of the beta 2 hat estimate in order to have this interpretation, which is different for the next two specifications. Okay. So when would you use this type of model? When your data looks like the one on the left, right? So this is a graph of the function given over here. Like I said, a Cobb-Douglas function might look like this, although the beta 2 coefficient will be positive rather than negative in the case of the Cobb-Douglas. So it would have a different shape than the one you see on this slide. But the point here is just to give you an idea of the circumstances under which a log-log model might be useful, right? And that is when a transformation gives you a straight line, as is the case on the right here. So a log transformation. So in the equation on the right, we just took the natural log of the equation on the left. And when doing that sort of transformation gives you a linear relationship, then a log-log model might be appropriate for that estimation. Right, now let's look at a log-lin model where you have the y variable logged, but the x variable remains unchanged. And this is useful for looking at growth rates, right? So in the example given here, you have log of y equals beta 1 plus beta 2 t plus u, and t over here, t over here denotes time, right? So the way to interpret beta 2 is that it is the percentage change of y for a given unit change in t. So there's an example given at the bottom, and this could be useful for, you could use this model on the data that you have in your assignment, for example. If you're interested in looking at growth rates, you can model growth rates looking at that. It's a particular type of growth rate. As you might be aware, if you're doing finance courses, there are different ways of estimating growth rates, of determining growth rates at least. There's internal rate of return, there's compounded growth rate, there's CAGR, etc. So this is one way of estimating a growth rate. So how do we interpret the beta 2 hat over here? Well, if t increases by 1 unit, in this case we have annual data, then on average real GDP grows by 3.13%. So notice here we have to multiply by 100 to have this interpretation, right? And this is an average growth rate, right? As suggested here. This is what you're estimating here. Average growth rate of 3.13% for GDP. All right, now let's look at and here's just a graph of a log-lin model. So the blue data is associated with the scale on the left. This is real GDP measured in billions of rands, right? So it ranges from under 500 billion to about 3 trillion, similar to the data you have in your assignment, but I think this might be a longer series. The orange series is the logged version, and that is given on the scale on the right, right? And that ranges from around just over 12.5 to about 15. Then the straight dotted line gives you the regression estimated model, okay, run on the logged Y, the logged GDP. Again, this is the average growth rate for this series, okay. All right, now let's look at a lin-log model. So lin-log model is where you have the unchanged Y variable regressed on a logged X variable. Here the interpretation of beta 2 is that the beta 2 is the absolute change in Y for a given percentage change in X. And as an example of such a model, here you have GDP regressed on the log of the money supply. And here again, you have to transform the estimated coefficient to have the correct interpretation. You have to, in fact, divide it by 100, right? So the way to interpret this is that for a 1% increase in money supply, GDP increases by 25 rands, okay? And of course, here we're assuming that GDP was measured in rands. If GDP was measured in millions of rands, then it would be a 1% increase in the money supply is associated with a 25 million rand increase in GDP. Again, important to note, you have to divide the beta 2 hat estimate by 100 in order to have the proper interpretation. Okay, the other functional forms that I'll just sort of present you. We're not going to discuss this in much detail. This is called a reciprocal model. These are just transformations of the variables, whether it's y or x or both. In this case, we're just taking the inverse of the x variables. What's useful about this model is that it approaches some asymptote, right? So here you have three sort of versions of the model. In the first version, you have beta 1 is larger than 0 and beta 2 is larger than 0. And the asymptote is effectively determined by the value of beta 1, right? So you can see over here. And by asymptote, what I mean is that this, the data, the estimated model, never goes below the value of beta 1, right? So it approaches beta 1. So no matter what beta 2 is, it will never be lower than beta 1 for panel A over here on this graph. In the case of panel B here, you just have a beta 1 value that is less than 0, right? So that's possible too. And in fact, you can have that in the Phillips curve, for example. And again, here the data series the estimated equation is such that it never goes below the value of beta 1. Now, of course, you can also have the asymptote above the series. In this case, so the example is given here in panel C, where you have beta 2 negative and you have beta 1 positive, right? So here the asymptote lies above the function, okay? And the function can approach the asymptote, but it never crosses the asymptote, okay? So if you have a data series that sort of looks like this, then it's useful to apply a reciprocal model. And of course, another example of this is given in the textbook, where they use the example of child mortality. So child mortality is regressed on some measure of income, right? Perhaps per capita gross national income. Again, here you have an asymptote, which one would hope is at 0 or as close to 0 as possible. Yeah, okay, so have a look at that example in the textbook as well. Okay, two other functional forms very quickly are the logarithmic reciprocal model. So here you combine the reciprocal model with for the x variable with a logged y variable. And this image, at least, you might recognize or might look somewhat similar to a production function, right? So in the case of a production function, you have a initially rapidly rising relationship between y and x, right? Almost exponential, and you can think of this as a sigmoidal sort of function, where initially y rises rapidly as x increases, and then at some point diminishing return sets in, right? So and this idea should be familiar to you from your macro courses, right? Where in some production process, adding more production factors initially might expand output exponentially in the beginning, right? But at some point, marginal returns kick in, and additional production factors don't yield commensurate increases in output, right? And so that's the flat part of this curve. Then there are polynomial models. So on the graph on the right, you have the familiar marginal cost and average cost functions. And those would look something like the equation that you see up there, right? If you were to estimate this empirically, you have some kind of polynomial function like that. If you have a negative value for x2, then of course this thing will turn, your graph will turn around and look something like that as well. But in either case, you have one turning point, right, for this data series. And if you have data that look like that, then the specification would be useful. One example of this might be the relationship, say, between income and age, right? In which case you'll have a negative association for the squared variable, the squared x. So we expect income to increase as age increases, right? Up to some point, maybe that point ideally would be at retirement age, right? After which, unless you're extremely wealthy and you continue getting richer and richer, your income starts to go down. Okay, so just some points on functional specifications. So we just very quickly went through some of these specifications in this last section because this becomes a lot more important and once you start estimating multivariate regression models, right? But just a few pointers to close out the section. So your functional form will largely depend on the underlying theory. Now, of course, in this course, we're dealing with bivariate models. There's almost no theory except for the handful. Two of them you'll find in your assignment. And even if you look at the way these models are estimated in research, by looking at the review papers that you're supposed to summarize, you'll see that even for those two models, typically we don't just estimate bivariate relationships, right? And that is because we have to control for other factors always. Even though we're interested in the relationship between two variables, it's important to at least attempt to control for what we call confounding variables, other variables that also influence y, other than the x we are interested in, right? And the variables you include in your model, as well as the functional specification, the form that your function is going to take, will depend on the underlying theory that you are using in your estimation, right? Also, be careful about comparing the R squared between two different models, okay? Especially if the dependent variable is already is different. Now, in cases where the independent variables take different forms, the R squared for those models are more comparable. I would apply the same caveat and suggest that you don't solely rely on R squared as a measure of whether one model is better than another, but look at the totality of what it is you're doing. Okay, so you're guided by underlying theory when choosing a particular functional form for your model. Consider things like rates of change, whether you are looking at elasticities, trying to estimate elasticities, for instance. Also check whether the estimates that you arrive at are in line with what you expect, right? With what theory might suggest, or in terms of what might be reasonable. Again, practice caution when making judgments about R squared values as a criterion for determining the appropriateness of a particular specification, and don't rely on this. Certainly, don't rely on this only, right? And the last bullet point, it talks about various tests. Later on in your third year course, you'll start looking at specification tests. And this can take various forms. Okay. All right, thanks for your attention, everybody. It's been seemingly long, even though it was shorter than usual, a seemingly long semester. And no doubt a trying semester under the circumstances. Do get in touch if you have any questions regarding your assignment. All right, see you soon.